Cloud computing replaced physical server racks with elastic, consumption-based models. This elasticity created an illusion, a false sense of infinite, frictionless data capacity. That illusion quickly runs into financial reality. High-performance cloud databases and data warehouses charge severe premiums for compute-adjacent storage and active memory footprint. As operational tables bloat, costs escalate without bounds. This cost differential comparison table maps storage tiers against their monthly gigabyte pricing. Notice the massive disparity. In-memory, high-performance database tiers sit between $2 and $5 per gigabyte. Down at the bottom, deep archive tiers cost a fraction of a penny. Faced with that math, IT teams experience the architect's temptation, the overwhelming financial incentive to rip historical transactions out of expensive operational engines and migrate them to cheaper storage. The immediate instinct is to take inactive records and push them directly into standard cloud object storage, like Amazon S3 or Azure Blob. The baseline assumption is that simply relocating the files constitutes a complete archiving strategy. Moving records without a semantic framework creates a disconnect between the physical file and its business meaning. Pursuing raw storage savings without integrating a formal information lifecycle capability generates immediate financial relief, but the operational debt begins to accumulate. This diagram shows the complete total cost of ownership equation for enterprise archiving. Raw storage capacity is only a fraction of the actual cost. If operational patterns require frequent reads, you trigger the remaining variables. Per request API fees and gigabyte retrieval surcharges quickly eclipse baseline savings. These low baseline storage costs often trigger a psychological trap, the hoarding fallacy. Because holding the files seems cheap, organizations keep all data indefinitely. That accumulation creates immediate legal exposure. During a lawsuit or audit, e-discovery mandates force legal teams to search petabytes of uncurated historical documents. Privacy regulations like GDPR strictly enforce data erasure. If personally identifiable information is scattered without metadata tagging, executing erasure requests becomes mathematically impossible. Flooding internal large language models with uncurated, outdated historical data causes retrieval context pollution, directly leading to severe system hallucinations. Without rigorous curation, inexpensive cloud storage inflates operational liabilities and actively poisons future enterprise analytics. Solving this total cost and risk equation requires a specific architectural separation, explicitly decoupling the physical storage of the data from its semantic governance. This split-screen model illustrates that separation. On the left is the data plane, which handles the physical resting place of the files and query execution. On the right is the control plane, the semantic brain governing the entire system. The data plane deploys a dual representation strategy, storing migrating data in two distinct structural formats. The first is the immutable source representation. This retains the exact, unaltered payload extracted from the source application, providing strict evidentiary integrity. The second format is the open normalized representation. The raw data is converted into self-describing columnar formats, like Apache Parquet, providing massive compression ratios and immediate analytical readiness. The control plane holds absolutely zero raw business data. Instead, it exclusively manages the metadata catalogs, the business glossaries, the schema registries, and attribute-based access policies. Isolating that semantic intelligence inside the control plane ensures the files sitting in object storage remain cataloged and discoverable.
In legacy archiving, accessing old records meant waiting days for an IT department to physically retrieve tapes and restore them to a staging database. Modern architecture bypasses this entirely. The replacement mechanism is serverless direct query, which keeps deeply archived cold data actively visible. This flowchart tracks a user query in real time. When an auditor searches for a transaction, the request hits the control plane, which maps the business logic to the exact physical file paths and passes those instructions to an embedded serverless query engine. Because the Parquet files store their own schema definitions directly in their index footers, the query engine can interpret the data structure immediately, completely bypassing active operational databases. Instead of scanning the entire archive, the engine executes targeted HTTP range requests. It fetches only the specific byte range needed for the query, instantly skipping gigabytes of irrelevant data blocks. The execution runtime provisions instantly for the query and shuts down the moment it completes, resulting in zero standby compute costs during idle periods. By combining self-describing formats with serverless execution, the architecture provides reliable, on-demand visibility into historical data using the commodity infrastructure that hosts the physical files. The lifecycle of an enterprise record eventually reaches a final phase, frequently ignored in cloud environments: the mandate to permanently destroy expired data. This data lifecycle taxonomy chart maps the migration path. Data flows down from high-cost active data into warm data through the governed archive and inevitably reaches the final stage: defensible deletion. Defensible deletion is the systematic, automated execution of business retention schedules. When a record expires, the system permanently erases it and generates a cryptographically signed audit log to prove compliance. Business timelines are sometimes interrupted by active litigation or regulatory audits, requiring a legal mechanism known as a legal hold. The control plane allows compliance officers to flag specific data sets. Applying a legal hold instantly freezes the background disposition timers for those exact files. This mechanism protects the enterprise against claims of data spoliation during a lawsuit, while allowing the system to legally purge irrelevant historical data. An archive lacking automated, verifiable disposal creates an ever-expanding footprint of legal exposure that outlasts its technical utility. Translating this technical architecture into reality requires a shift in how the enterprise operates and assigns ownership. This maturity matrix illustrates a phased implementation roadmap. The enterprise moves incrementally from a crawl phase, focusing on basic operational offloading, through to a plus phase, where the governed archive actively grounds generative AI contexts. Success in these phases is measured by precise indicators. The primary financial metric is achieving a greater than 40% reduction in legacy database total cost of ownership. The primary compliance metric requires achieving 100% verifiable cryptographic audit coverage on all purged objects. To hit those metrics, data lifecycle management cannot operate as an isolated IT infrastructure project. It must function as a cross-disciplinary workstream, governed jointly by enterprise architecture, legal counsel, and business domain stewards. This aligns the organization around a unified architectural principle. Enterprise data must reside in the lowest cost tier, formatted in open standards, governed centrally, and systematically destroyed upon expiration. When engineered correctly, cold cloud storage functions as a governed, analytically active layer of the data lifecycle, preserving both context and capital.